Really need these two to get started. Actually, thank you, Dee. Sorry, I always forget to record. So
No worries, I got you.
Welcome to the session. Thank you. We're just doing a little recap. The goals are to just learn joins and understand the common problems like errors and cardinality. And as you may recall from last time, the SQL statement that we worked with was select, the most common one people use. And if you present these clauses in the right order, you can pretty much get what data you want usually. Yeah, cool. Let's press on then. We're going to talk about joins today and how to connect them tables together, which is pretty often useful. But before we get into that, it's always a little good to understand all the background and the whys and everything. So I want to present you with an analogy that you may find helpful when thinking about SQL and writing code in SQL. And that's just to imagine all your tables as if they were spreadsheets, right? A lot of us are maybe more familiar with using spreadsheets, Google Sheets, Excel, than you may be with a database. Database, is kind of arcane and uses code, and the UI looks like really old in some cases. So, but you probably use Google Sheets every day, and you know a lot about it. So if you're thinking about it with that analogy in mind, a select statement is basically a filter on columns. And a where statement is a filter on the rows, and the from statement just tells you which sheet you want from like the folder of all your sheets, right? So you're just doing normal Excel stuff. You just have to write it out in code in a way that's less elegant than just clicking the buttons in Excel, right? And order by, again, you know how to do that in Sheets. I'm sure you just right click and off you go, right? So if you think as every table as a spreadsheet, that'll help you when you're thinking about how to join. And when you join across tables, you are essentially taking your two spreadsheets and merging them into one spreadsheet by copying and pasting, essentially, so they're side by side. But in order to do that effectively, you need to identify a column that is matching between the two spreadsheets. Otherwise, there's really no point putting them together, right? So joining then, I just described it here. It's the act of taking these two spreadsheets or SQL tables, right? Stitching them together, and then you have one spreadsheet with all the columns from both. In order for that to work, though, you need to determine which rows from one spreadsheet will match which rows on the other, right? Without a matching principle there, you just kind of have a pointless mishmash. When you identify those columns that you want to join on, those are called you describe it as joining on the columns, right? So, for example, you may know that the name, you have two spreadsheets, one with names and addresses and another with names and genders. The names match, so you could match them up on name, right? I'll give you some more concrete examples in a minute. But before we go too far into how joining tables works, I thought it might be useful to step back for a second and think about why you would even want more than one table on a database. In principle, you could just make a giant table with every field that you ever care about in it, and you're off to the races, right? Like, why bother with more than one table? Obviously, your one table would be very, very large, but whatever, the database is large, so no big deal, But there are a couple of really good reasons to have more than one table, and I think it's nice to understand those so that you can understand the decisions that went into making the database you work with the way it is. So there are certain limitations on a single table, such as it can only really express a single set of relationships. You obviously, everything in your database is related to everything else, so you can express all of those on a single table, but it does mean that you need a massive amount of complexity on that one table to do it correctly. A single table, and that's because, a single table can only effectively or efficiently express data at a single level of cardinality, right? Every row on your table represents a certain kind of thing, and a table can only have each row represent a single kind of thing. So like persons or races or addresses, if you put them all together, then every row represents a person, race, address set, and you will end up with many, many, many rows to represent all the possible combinations of those things. So your table starts to grow in size massively, and you no longer are efficiently depicting the data. And then that leads into the last thing, which is when you want to modify this data, it becomes way harder. So if we have a row for me in my first address and a row for me in my second address, now when you want to update my name on the database, you have to update my name in two places, right? And now just imagine if you have a row for me, my address, and my races. Now you have maybe 3 rows for me and maybe many more rows for everyone else. And now you want to change the value of white to Caucasian. You have to go through every one of those cells where it says white and change the value to Caucasian, which is way less efficient than if you did it differently. So just a little bit of database design stuff there. And that's one of the more interesting parts of SQL. So I thought I'd share it with you. And let's maybe look at an example of one. So when you're joining on a database, as you recall from last time, we talked about how it's really important to always have your schema in mind and know which columns there are, what their data types are, and so forth. In working with databases, those relationships are depicted in what's called an entity relationship diagram, sometimes also known as an ERD. Let me zoom in a little so you can see this better. Just fix. Just pop you over here. You can see it here. So an entity relationship diagram. This is not a very great example because I didn't draw all the lines and everything, but the idea is it tells you what all the columns are and the tables names are. And in this case, I've even shown you an example of the data in each column. So I just want to maybe take a minute to talk through what this table setup is and how it can be joined to itself. And if you're interested, you can actually see these exact tables in the SQL sandbox that we spun up. So you'll see, address, person, race, and so forth there. Okay, so just talking through it, we have one table for persons, and we've got me and my household in there. So we have our names, our phone numbers, but note also that each person has a numerical ID. Anyone want to hazard a guess as to why we use numerical IDs and not just names? Yeah, you're right. We use it because people can have the same names, right? And we want a unique identifier for those people. So that's why you'll see so many different IDs on databases, because the other values in the columns do not guarantee uniqueness, whereas an ID can guarantee that, right? Now, okay, we have persons, and you'll notice they also have gender IDs and address IDs. Let's look at gender ID first, right? Obviously, it's pretty easy to interpret M, F, and so forth and understand what they mean. Why wouldn't we just write the word male, female, and so forth in these columns? Instead, we have to take these values and use them to match to the gender lookup table over here. So if you were to match on male, you'd put, oh, male is the value for that one, and so forth. The reason we do this has to do with that efficiency we talked about before. If you wanted to, for example, change it so that all the F's meant girl and all the M's meant boy, in this setup, if you didn't have a lookup table, you have to change every row one by one. Here, I can change all of the M's to mean boy just by changing this single cell. So that gives me a lot more efficiency if I need to update that kind of thing. Like if CDC comes down and says, all of a sudden, we're going to change that. Right? These IDs can also be used to look up addresses. Over here, we have the address table, and you'll see that the address 123, actually, there are several addresses that match to 123, right? There are 2 addresses with address ID 123. And so those are the different addresses that correspond to this person. Next, I want to draw your attention to these 2 tables down here, which are the person race and the race lookup. Person race is what we might call like a matching table. You'll notice there's no race ID on the person table. Instead, we just have this other matching table for persons and races. There's a reason for this as well, because a person can have many races. I did it wrong with address. This is not ideal database modeling. In fact, this whole thing is a bit messed up for illustration purposes. But you did it this way because if I put every race on a row on the person table, I would need multiple rows for each person because a person can have more than one race. By using this matching table, I can insert, person ID 453 twice on this table to capture the fact that they have two races. And then I use their IDs for the races to go find the actual human readable value for that race. So 453 matches to person ID 453 on this table. And then you can match the race IDs. So we have 987, 981. And we can then realize, okay, Ashley, she's Black and she is American Native. Right? Good. Other things to be aware of are naming conventions for your columns. You'll notice in the gender lookup table, it just says ID and value. Some databases will do it that way, right? But for the race lookup table, it says race ID and race value. So you'll want to be aware of those so that you name your columns and so forth correctly in your queries and everything like that. Great. Any questions so far about the database and so forth? We talked already a bit about how to read this. If you're interested in a more complete ERD, you can see one here. This is the diagram for the lake house, and you can zoom in and you'll see it's got keys for where the 4 primary keys are. It's got lines to help you join across tables and things like that. Probably worth talking about this terminology real briefly. A primary key is a unique identifier on a given table. So in our example here, person ID is meant to be a primary key. It uniquely identifies each row. In some cases, a primary key can be composite, meaning that it has to be set up from across multiple columns. For example, on the address table, there's actually this is not a really good example because that is not enough. But the composite primary key is like the address ID, person ID, plus the street address, right? You have to have all 3 of those to really get a unique row from each. A foreign key is the key used to relate from one table to another. So we've got, this is the person ID, and then it's a foreign key over here. So it's a primary key on the person table, but it's a foreign key on the address table because it's just used to join over. And then we talked already about the relationships, and we'll get into cardinality down the road. Okay, I'm sure the moment you've all been waiting for. Let's actually write one. When you write a join clause, it's got the syntax you're familiar with. You've got select, you've got from, and then you just add join to the from. You're essentially adding more columns to the set of columns you select from. So all you got to do is write join, and you put the table name you want to pick. You say on, and you provide the columns you want to match on. So I'll give you an example right here. Here I've got my person table. Fun fact, if you just highlight it and run, you can run just a subset of your code. So this is only running select from. So you can see the output here. It's the people, right? And we've got some nulls and so forth. Now I can join, and you'll notice again the word join. We've got the name of the table, in this case address, and then I mentioned the columns I want to join on. The address IDs, I say they need to match, right? So we'll run that. And now you'll see the previous table had, I think, about 8 rows, and now I have 10 rows, and you'll see there's duplicated people, and that's because Ada has 2 addresses. She's got 452C, and then she's got some kind of blank address in Denver, right? So since there's a difference in how many addresses you can have for each person, you'll get more rows when you join like this. But the idea is we matched on the address ID and pulled up all the addresses for the given person. Cool. I mean, pretty straightforward when you say it that way. Any questions about it? How that works so far? Maybe some pro tips for how we did it there. First off, this is really, really important. Just use some aliases to make your joining a lot easier. You'll notice in mine, I just aliased my tables with 1 letter. So the person table I can refer to as P, and the address table I refer to as A, so that when I have to say which columns to join on, I can just type in P.A address and A.address. If I didn't have this, I have to type out the whole info mart, SQL, sandbox. It gets much longer and much more annoying. Just pick some aliases. I just use something that reminds me of it, usually the first initial of the table name, and that does the trick. Other thing to be aware of, you can join on multiple columns at the same time if you want to. Here, for example, I've got my address IDs, but I can also say, and let's make sure that the person IDs match. I don't know why they wouldn't, but they might not, right? Okay, so we can run this now, and with any luck, it should give me the same number of rows. Oh, a little less now. I wonder why. I'd have to think about that. Let's look at those. This person ID doesn't exist, so we wouldn't have pulled that up in our match, right? So just an example there. Okay, so you can do this. This can be helpful if you want to filter or create a more constraining constraining join. Good. You can also use like a direct filter in the join instead of like it uses similar syntax to joining on multiple columns, but you can join in a way that filters things out in the middle of it. So here I said, okay, the addresses have to match, but I can also say, and let's make sure the person ID is equal to 1, 2, 3, right? This is the person ID I want. So you can provide any condition you want in this join clause, almost like a little mini where clause. And by doing so, you are filtering sort of in line without having to go to the where clause later. Do that. And then another thing worth being aware of is you can join to any table or view. I mean, sometimes you will fail because there's nothing to join on, but in principle, the join clause will work no matter what you point to. And it's important to remember that when you write a select statement, the output of a select statement is a table. It's not a table stored on the database. It's a table stored in the computer's memory, but it is nonetheless a table. So you can join to a select statement. So if I wanted to, I could write select star from gender, or let's do this correctly, info mark equal sandbox, and then here we'll pull up the gender, right? Gender lookup. Let's give this a name. Oops, sometimes my names are too short. Okay, and then we will join, and instead of putting a table name, I'll just put join, and I'll give it this table that we created. Okay. Get this part off so it's the part. And now this whole element here is treated by the code as if it was a table, because that's what it does when you run this part of the code, right? That's a semicolon, sorry. And so then you give this part of the code an alias. Let's call it PA for personal address. That's what it pulls up, right? Oops. And then you have to say what you want to join on. So we're going to do ge.id is going to equal, because that's the gender table, recall, and then this thing has a gender ID in it. Right? Let's give it a try. So here, you'll notice the first thing in my from statement is the first set of columns, or the one on the left. So I'm pulling up all the genders first. Well, this not exactly ideal, but the rest is persons and addresses, just like we saw as the output of this subquery, right? So this is a way you can like nest queries. I mean, in this case, kind of pointless, but you can do this for other reasons. Maybe you want to filter, or you want to join onto a small subset or something like that. So you don't always have to save everything as tables. You can just join to select statements, which is kind of cool. And then last, you can join a table to itself. This is sort of weird and probably don't often want to do this, but it is technically possible. So in this case, we could do, for example, let's join from the address table to itself because it has two sets of IDs, right? So you could do info mark SQL sandbox dot address, call that A1, join info mark SQL sandbox address, call it A2, and then you just say, let's say the A1 person ID, we want that to match A2's address ID. Maybe they'll match at some point, like some crazy look. So now I'm just finding all the rows where the person address matches the person ID matches the address ID. I see we don't often want to do this, but you might have cases where there's two columns on a table and you want to check if they match. And you can obviously, and this is one way you might do it. You can do this in where clause as well, right? Where column A equals column B, but here we're doing it via join. And it's the same idea. Notice though that I got 9 rows for this where clause, for this join, even though there's actually only 3 rows where the addresses match like that, right? It's this one, this one, this one. But because the table is being joined to itself, it takes all possible combinations of those. So I got 9 rows at the end. That's a pretty important thing to be aware of with joins in general. They are returning to you every possible combination of matches in the matching parameters you provide. So if I want the addresses to match the persons or the addresses to match the addresses, I need them to, every possible match will show up. So if there's more than one match, it's going to show me both pairs. And in cases where you're matching to yourself, you're going to get lots of weirdness happening. And you can, in fact, just match the same table onto itself with the same columns. If you do this, it will just run and run. Oh, no, it didn't run and run. What did I do wrong? Oh, yeah, we have to actually match the same table to itself. And in this case, this one should probably run. Dang it. Sometimes I try to create errors and I don't do it. Anyway, when you create a join to yourself, do your best not to create an infinite loop because you have that risk there. Good. All right, well, so far you should be feeling maybe a little better. You know how to write a join statement now, so good job. Let's press on a little because there's a lot of more complexity to this. There are different types of joins, and this is, I think, where people start to get most confused. So probably 3 are the main types of joins that you care about. And the way they're differentiated are in how they combine the rows from the 2 tables. The default join that you will get if you just write the word join and go for it is called an inner join, and it only pulls rows that have matches on both tables. So, excuse me, let me show you the examples. So, this was our address to person, right? Oops. Okay, so you'll notice, right, this person, this address has no matching person, right? 678 has no matching person. And this person, Moira 9098, has no matching address. So if you start with address and then you join to persons, you're using an inner join and you're matching address IDs. So that means any address ID that exists on A but does not exist on P should not come up, right? So let's give this one a run. And which one was the one that we don't want to see? 678. And you'll see in our table of matches, there's no 678. So what I've done, and maybe done without knowing, is I've filtered out all the addresses that don't match. And the same thing I've filtered out, if we kind of show you on this example here, so you can see a little better, Moira didn't have an address, right? So when I run this, Moira is not in my output. So if I were running a report on people and I just wanted to pull their addresses, I now will never know about all the people who don't happen to have addresses. So if I wanted to know about those guys, I need to not use an inner join, because an inner join is sort of a de facto filter on these rows, which filters out the ones that have no match, right? So that's one thing to be aware of. Often inner join is what you actually do want, right? I don't care about people who don't have addresses if I'm trying to map everyone's addresses onto some kind of visualization. If I'm trying to do some kind of completeness report or give more statistics on addresses in a population, it might matter to me that some people just aren't known. Good. So that's an inner join. It's the default join. It's what you're going to be doing without knowing it. So good to be aware of. It's often actually what you do want, but obviously you want to be cognizant of what you're doing. Now, the other kind of join, which kind of solves the problem we just saw, was a left or a right join. So you can do that, and let me kind of clean this up. Let's just pull this thing up since it's a little care about. So in a left or right join, you keep all the rows from one table, and If they match, great, pull the rest. If they don't match, just put nulls. So if I wanted to, I put this one to be left join. And now we're looking up all the addresses, but Moira will be in this list with any luck because Moira doesn't have an address, but that's fine. All right, so here's Moira. You can see she has no address ID, so she was filtered out before. But now, when you look at her address data, it just has nulls because there's no address data, so no surprise there, but she's still on the list, right? Now, one thing that often can be tangling people up is what's a left join, what's a right join. It's a little bit of a misnomer, but if you think about the left right, you can think about it like as if they were here, right? So the left table is the first one, and the right table is the next one. Obviously, I'm putting on different lines, so it's more like top or bottom join, I guess, but you can still see the idea. What does not matter is the order here. So this might seem like, oh, we're doing something clever here, but if I change this to start with the A and then go to my other table, this is irrelevant. We're still going to get the same results. Moira's still there, right? Even though she has no address, and that's because this is only telling the system how to join it. The order of the tables is what matters for left, right. And speaking of, if I make this a right join, it's going to pull all the rows from the address table, and then it'll match them over to the person table. So if you're a person with no address, you're not on the list. But if you're an address with no person, and you'll recall there is one such, it's this 678 on Cool Avenue, then you will pop in, right? So let's run this thing. So Moira's gone, and you'll see there's a person row with all nulls. That's 678 Cool Ave, where apparently no one lives. That's sad. I thought there were more cool people. But you get the idea there, right? So left, right is the common way to get all of them from one and only the matches on the other. 9 times out of 10, you just use left because that's the order of your thinking, and you need the one you're going to join on first. But if you want to use right, more power to you, totally possible. By the way, you'll see I keep getting this syntax error about end of input. If you have multiple lines of code, you can separate them with a semicolon, and then that tells the system that these are different sets of scripts, so it evaluates them each independently, and that really eliminates the error, even though I have multiple code sets. Okay. Too many tabs. All right, let's go. Okay, we did inner, we did left. The other option is full outer. So obviously, using my guess, full outer just matches everything to completely. So full outer. In this case, we're going to have Moira and we're going to have Cool Ave in the same query because it's just taking them all regardless of match. It matches them if possible, but if there's no possibility, it just puts them on there anyway, right? So we got all nulls Cool Ave, and we got Moira and all nulls for the address, right? So that one can be useful if you just want to smash the tables together and get everything. I don't not found it always to be useful. Usually you care about one thing more and you just want to find its matches. Okay, good. I also included here just some diagrams. Sometimes it's nice to have a visual. These are, I'm sure you already had this in your mind. These are just Venn diagrams, right? The inner join, take the center, left join, take the whole circle, and then enjoy your overlap. Right join, same story, full outer, you just take both circles. Right? And of course, all these are on our glossary if you ever want to put them on there. Okay, cool. Now I'm just going to kind of go through some of the common mistakes people have with these. So one is mismatched data types. And if you have the wrong data types on your table, then you will not be able to join effectively, right? I was lucky here because address IDs are both numbers, right? But if I were to try to join the address ID to the name, this, obviously I'm not going to get anything because there's no match. But I'm not just going to get nothing. I'm going to get an error along the lines of there's no matching signature, or it's type mismatch or something like that, because one of them is an integer, 64, or a number, and another is a string. So you just can't join these even if you want to, right? You can, of course, fix that if you like. You just have to modify the data type of one side. Usually it's best to go from integer to string so that you go from less permissive to more permissive. And then if you run this, now you can join them. Because this is an outer join, it worked, but you'll see there's actually no matches for anything. So I just have the full 14 rows of everything. Ulav got nothing, Moira got nothing, but Ashley also, she apparently doesn't live anywhere because there's no match for her name and the address ID. Right? And that actually brings us to the other common problem, which is joining on the wrong fields. If you join on fields that don't actually match, you will get nothing, or you will get erroneous data. And in this case, because this outer join wasn't even obvious at first glance, maybe. So if I join here, this perfectly fine query will run, but then you'll just get no data. So if you're confused why you joined on something and all of a sudden all your data disappeared, probably want to reevaluate which fields you're using in your join so that you make sure you've got the right ones. This is another one that comes up often, is the ambiguous names in the select clause. I've just been selecting stars, so it's been pretty straightforward, but more likely than not, you don't really want all these. So let's clean this up a little bit, and I'll show you how you can get this error. Often in your select statement, you have things like name, you might have person ID, you might have, let's see, phone number, and maybe street address, right? Okay, great. So we've got our really cool query. We've got some key factors we want to pull. Oh, let me fix this part. All right, so when I run this, I'm going to get an error that says column name person ID is ambiguous. Obviously, because the computer is very persnickety, you have to tell it exactly which fields to pull. And you'll see there's a person ID on the address table, and there's also a person ID on the person table. If you just tell it pull the person ID, it's confused because that exists in two places, and it doesn't know which one to pick. So you just have to be a little clearer with it. And this actually is a good habit in all your select statements, which is preface the name of the column with the name of the table you want to draw it from. Again, alias is big help here. So now that I've specified each of these, the system knows, oh, he wants the person ID from the person table, and off we go, right? If you just make a habit of always doing this kind of prefacing, not only does it keep your own head straight about which tables, which columns you're pulling from which tables, so you don't get mixed up at all, it also ensures you will avoid that kind of error. Of course, to be careful, if I had put the A address ID, then Moira will never join this query because I am not pulling her. She doesn't have a person ID on the address table. So even if I did a full outer join, actually, I might get Moira, but I might not. She's not gonna like show up properly. Let's see. So let's view these ones. So there's Moira. Okay, it did work good. But she has no person ID, you see, so that is not correct. Moira does have a person ID. Her ID is 9098. It didn't pull it though because she has no person ID on the address table. Okay, good. And other error is one I kind of alluded to before, which is defaulting to inner joins. If you just use inner join uncritically, you will accidentally filter stuff out and then be surprised when you get less results than you expected or different results than you expected. So just always be aware of the inner join that you're doing by default. Okay. Any questions about SQL joins, inner joins, left joins? Okay. Then next topic, last one for our day today, is cardinality. So this is a really important one to keep in mind when you write queries because it can often create problems for you if you're not paying attention. And it's actually quite hard to wrap your head around sometimes and creates a lot of decision points in your work. So the way you can think about cardinality is it's the what each row on a table represents, right? So each row on the person table represents a person. Each row on the address table represents an address. for each row on the race table represents a race, and so forth, right? Now, in the setup of the database, that should be captured by the primary key, which is the unique identifier, right? So if each row is a person, then each person ID is a unique person, right? But you'll notice that doesn't always actually come through properly. Here, the street address 452 East Street, A, Thousand Oaks, is on 2 lines, and it has different address IDs. Thus, this table is not really well built. It has a bad primary key, so that duplicative data shows up. Even though each row is meant to represent an address, it actually ends up representing like a person address pair. And so this row is different than that row because 789 lives at this address as well as 123. So you want to bear in mind not just what you imagine each row meaning, but also how that's actually enforced and expressed on the database at a technical level by using it in the form of the primary keys. Right. Now, that's great. Okay, so you know what each row represents, but now when you're connecting tables together, the conceptual identity of each row on each table can have a different relationship to the rows on other tables. So, for example, each person can have multiple addresses. Each person could potentially have multiple genders over time. They can have multiple races, and so forth. So these are like many-to-one relationships that can occur on a database and create confusion when you are writing queries. So let's just look at a few examples. You can have, okay, one-to-one relationships. In principle, person to gender should be a one, actually, it's not exactly right. I don't think there are any one-to-one relationships on this table right now. Person to gender is a many-to-one with many one, let's say, okay, it's one-to-one in this direction, actually, yeah. So you can call that a one-to-one. You obviously can have many-to-one. Like we said, there are many addresses for every one person. Then you can have many-to-many, but there are many races that can each be applied to many persons, right? So in that case, it's a many-to-many, which is a key reason to have an intervening table like this one, so that you can navigate that instead of having all of them on one column. The reason you need to be aware of this is because if you start joining across all these, you start gaining rows on your query, and maybe to your detriment, and you're going to get surprised by all the duplicates you create. So let's do this. We'll start with we're just going to select them all. We'll start with the address table, but then let's also pull up the races for all these people. Right? Person race. Let's give it the name PR. And we have to give it the matcher, so person ID, and then we'll make that match the person ID on PR. Great. And then we'll join this one over to look up the actual human readable value. So sandbox, and now we're looking at the race table, race lookup table. Give that one R on R dot race ID equals the R dot race ID. And why not, for good measure, we'll throw on the gender tables too, so now everything is linked up. And this one you have to be careful because it's called ID on here. So ID has to equal the dot gender ID. Okay. So notice we started with 6 people, right? If you join all these, you now have 10 rows. And you can kind of see them growing over time. Yeah. So especially if you use an outer join or a left join, it will grow even more. So there were 10 matches with address, and then you can add rows and see if it goes up or down. So hopefully I think all the explosion happened at address. Good. So whenever, and this can kind of compound over time too, although this particularly this might not be the exact best example, but if you had a person with many addresses and many races, then when you go from person to race, every possible combination will come through. So you had 2 addresses and then 2 races, but you will have 4 rows for that person at the end. Which I didn't visualize here, but you get the idea. All right, very good. You can see I kind of explained that here. Ignoring cardinality, yeah, like I said, can create a lot of duplication. Um, and I'll give you an example of that person. Now, the way to fix this is to always keep your eye on what you want your resulting data set to have as a row level kind of concept, right? Do you want every row on your database or your data set to be a person? Should it be the event of someone getting a vaccination? Should it be a facility's air quality? Should it be the air quality of a given month at a facility, right? Each of these different ideas has to be managed differently when you're joining across tables. And you just always want to keep your eyes on the prize as to which one you really want this to be, right? And whenever you join over to a table where that isn't the right cardinality for that table, you need to do some magic to get the right cardinality out, right? If you want to get just the most recent address, right? Or if you want to sum up all of the days worth of air quality data to get just a month's worth, right? You're going to have to do something to get the data at the right level of granularity, at that right cardinality. That magic is the aggregate functions. I would talk about those next time, how to like group things, sum things, average things, so forth. And that's how you can flatten cardinality and get the right data set at the end. Okay, cool. Last thing I just wanted to mention on side, there's another join kind of strategy. It's called a cross join. This is when you join the 2 tables, but you just don't care how they join at all. You just join every possible match. It's a good way to get a massive table, so be careful. But there are scenarios where this might be useful, so I thought I'd mention it in passing here. Good. Probably heard me ramble on for long enough. Any questions, thoughts? All this, of course, recorded. We'll put it out. You've got the glossary here. These tables are all in the SQL Playground. If you want to hop in and write some queries, feel free. Kevin, were you just waving, or did you have a question?
No, sorry, I meant to just wave.
Well, thank you. I appreciate the waves and everything else. I will just wanted to say next week I have to take my daughter to camp, so I will either have to do this call from a very loud place, or we might push it a week into the next week. So let me think about that a bit, and I'll let you all know. But I'm excited to get into the aggregate functions next time. All right, guys, have a great rest of your day. Thanks for joining us.